Okay, so organic chemistry topic 10 and 20 review for IB chemistry exam. Now, instead of doing the kind of normal progression through the content, I think today what I'm going to do as a review is kind of do it instead of functional groups and then naming and then reactions. What I'm going to do is I'm going to do by types of reactions, and within each type of reaction, we'll address the naming and the functional groups that are involved in those structures. So that way we can kind of incorporate things together instead of segmenting them apart. And so that's what you're going to see today. And the first thing we're going to do is combustion. Okay, so combustion is essentially our exothermic reaction with O2. So this can apply to any organic compound throughout the entire unit. Generally, we focus on this with alkanes, alkenes, and alcohols. Those are the main classes of compounds that we deal with combustion reactions in here. And so, but they can work with any type of reaction. Now, for an alkane like CH4, we're reacting it with O2 to produce CO2 and H2O in what we call a complete combustion. Okay, so a complete combustion produces CO2 and H2O. Okay, and I'll balance that here. And the reason why it's called complete is because it's completely oxidizing the carbon and the hydrogen. In a combustion reaction, the carbon and the oxygen, I should say. So in these reactions, oxygen always completely oxidizes to -2. But what happens is the carbon may not oxidize completely. And so what you'll see here is because carbon is hydrogen is +1, carbon is -4 here. And when it bonds with oxygen, it becomes +4. So that's the complete range of carbon's oxidation, going from -4 all the way to +4. That's where CO2 comes into play. But when you have limited amount of oxygen, you get incomplete combustion, where that same compound might react with a limited amount of oxygen to produce different products. Always water, but the alternative carbon product may be different. Okay, so in this case, you might be making carbon monoxide or carbon solid as your products with limited oxygen. And you can see this based on the oxidation numbers, because here it's -4 and -4. But in CO, carbon is +2, and here carbon is 0. So you notice the amount of oxidation that's occurring is less because they're gaining less oxygens than in CO2, which is the maximum amount of oxygens that the carbon can gain. And so you notice that change in oxidation numbers kind of ties back to topic 9 with reduction oxidation reactions. And so keep that in mind. That's kind of a connection that you want to think about with oxidation numbers, of why it's called complete combustion versus incomplete combustion. And remember, these incomplete combustion products are dangerous. For example, carbon monoxide, CO, is a poisonous, colorless, odorless gas, which is quite toxic to humans, whereas carbon soot is a carcinogen. When breathed in or ingested, it can accumulate over time and be considered a carcinogen. So there are some adverse side effects to producing this incomplete combustion. And these alkanes and alkenes and alcohols we'll kind of address here a little bit, with their naming and their general formula, just to make sure that we understand what's kind of going on. An alkane's general formula is CnH2n plus 2, because every carbon has 2 hydrogens attached to it, and the last 2 carbons have 1 additional hydrogen to complete the chain of hydrocarbons here. So CnH2n plus 2. And the ending here is An. The E is not always automatic. That E only is put after the An if there is no functional group attached to the N. So pentan, it could be pentanol, it could be pentane, it could be pentanoic acid. But the last letter after the N, the E, isn't always guaranteed to be there. Alkenes are CnH2n, because with the double bond present, you no longer have as many hydrogens. You have 2 less hydrogens because the carbons are bonded twice to each other instead of bonding to single bonded hydrogens and carbons throughout the structure. And so you lose a pair of hydrogens when you do that. Alcohols are generally written like this: the CnH2n plus 2 OH. So it might be like C4H9OH or C3H7OH. Now, usually I think the IB will also write it as a structural formula if you're trying to identify what degree of alcohol it is and things like that. But if you're just saying any generic alcohol and it doesn't really matter, the isomer, then you just write it as CnH2n plus 1 OH. And that OH kind of signifies that there's a hydroxyl group attached to it. And this one is your OL ending. Instead of E, you put OL and you put the number of the location of the hydroxyl group as well in there. And so those 3 kind of structures for naming are important for organic formulas and things like that. Questions about that? Now, while combustion is a kind of a generic reaction, we also apply combustion into one other mathematical sense, which I'm going to talk about right now, and that is empirical formula using combustion. So with organic molecules, because they're carbon, hydrogen, oxygen, and maybe nitrogen based, we can do the combustion of those compounds to figure out what composition there is of each element in that compound. And so what you can see is something like this: CxHyOZ plus O2 yields. Now we're doing complete combustion because it's easier to keep track of all the elements in that complete combustion here. Now we can't balance it because we don't know the subscripts, but the problem will give you information to allow you to go toward the final answer. And so what they might tell you is the sample we started with was 0.255 grams of this unknown hydrocarbon with oxygen compound. And that when we reacted it with oxygen, we produced 0.561 grams of CO2 and 0.306 grams of H2O. And so what you have to understand is that there is a law of conservation of mass, meaning that matter can't be created nor destroyed, which means that the amount of carbon that's in this CO2 is the same as the amount of carbon in our unknown compound. And the amount of hydrogen in this water is the same as the amount of hydrogen in our original compound, because that's the only source of carbon and hydrogen in our reaction, in our reactants. And so if we can figure out how much carbon is in our CO2 and figure out how much hydrogen is in our water, then we could figure out how much carbon and hydrogen we started with in the original sample. And to do that, we have to calculate our composition of carbon in every sample of CO2. And so we go by molar mass. And so in CO2, for every 12.01 grams of carbon, there's 44.01 grams of CO2. That's always true. So no matter what sample of CO2 you have, that ratio is always true from the mass of carbon to mass of CO2. So we can apply that to our sample of 0.561 grams of CO2 to figure out the grams of carbon. Okay. And so I'll type it in, 12.01 divided by 44.01. To solve for x, we'd multiply by 0.561. And that gets us 0.153 grams of carbon that are present here of the sample of 0.255 grams. Now with the water, for water, there's 2.02 grams of hydrogen because there's 2 hydrogens for every 1 sample of water. So we'd apply the 0.306 grams of water, and then we'd solve for the grams of hydrogen. 2.02 divided by 18.02 times 0.306. And this gets us 0.0343 grams of hydrogen. Which means the rest of this compound has to be oxygen. And so if we do 0.255 minus 0.153 minus 0.0343, we get 0.0677 grams of oxygen. Okay. The reason why we can't do the oxygens on the right like we do with carbon hydrogen is because there's 2 sources of oxygen in our reactants. So we don't know which source is contributing that, so it wouldn't give us the right answer amount of oxygen if we did that. It wouldn't add up to 0.255. So we have to subtract the carbon and the hydrogen from it to get those values. Okay. Any questions about how I solve for those values? Okay. That's the hard part about combustion with empirical formula, because once you get to that part, the empirical formula aspect of it is identical to what you learned in topic 1 before. And so the goal here is to take each mass of your element and then convert it to the moles of each element, because you want to find the ratio between the moles. And so I'm going to divide this by their molar mass for each one. To get my results. Okay, so 0.153 divided by 12.01 gets me 0. Oh yeah, 0.0127 moles. Sorry, I was looking at my work from last Saturday, and I think I miswrote a number on there now that I'm looking at it. And then 0.0343 divided by 1.01 gets you 0.0396 moles of hydrogen. And then 0.0677 divided by 16 gets you 0.00423 moles. Okay. Once you have the moles of each of those substances, you divide by the smallest value. And the smallest value in this case is 0.00423. And when we do that, this divided by this we get essentially 3. And we obviously get 1 for the last one because it's the same. And we get 8. So what this tells us is our empirical formula is C3H8O1. Now that might be our molecular formula as well. We need to know the molar mass or the molecular mass of the compound to figure that out and what the ratio is. But we do know that the empirical formula is C3H8O. And that is a possible structure. That would be probably an alcohol or an ether. Those are really your two choices that would be able to have an oxygen and not have any hydrogen deficiency from it. Questions about that? Okay. Oh, sorry, I'll leave that up there for a second. Now, while alkanes are very stable because the bonds are very, very strong, they do have to react to allow you to kind of synthesize new products and things like that. And combustion is something that can happen with alkanes. It takes a lot of energy to start, but once it starts, it progresses it progresses spontaneously. Another way to make it reactive is what we call free radical substitution. And because the bonds don't want to break like double bonds or other bonds with like more polar bonds like a halogen bond with a carbon and things like that, that C to H bond is very strong. Is very nonpolar and very strong. So it's very difficult to break. So you need something that is extremely, extremely reactive to break it, which is where we enter the free radical. Okay. And so that idea of the free radical is something that has an unpaired electron, which makes it more conducive to break a strong bond like a C to H bond to resolve that unpaired electron in a species. And so the way we have found to make alkanes more reactive is we replace one of those hydrogens. That's why it's called substitution and not addition or oxidation, things like that, because we're substituting an H for, in this case, a halogen. And so we have 3 different steps for this. Our initiation step, okay, which is when we expose the halogen to UV light. And that UV light is the right frequency that breaks up the bond and splits it equally. Okay? Remember, this is called homolytic fission because it makes free radicals because the bond breaks equally. So the bond, the 2 shared electrons in a bond both go back to individual chlorines in this case. Once that occurs, propagation happens. And propagation is the method in which the free radical you formed seeks out something to remove that free radical, and it thus creating a new free radical in that case. It's kind of the chain part of this. And so if you're thinking about what's happening in this reaction, let's say this is like CH4 plus Cl2 to make CH3Cl plus HCl. What you have in your system right now is CH4 and Cl2. Well, a Cl free radical reacting with Cl2 makes no net difference, right? Because you're just going to make a new Cl free radical, but it doesn't really progress things through. So what that Cl free radical does is it reacts with the other species in there, and that is the CH4. And because the C is surrounded by hydrogens, the Cl has to remove a hydrogen. It can't attack the carbon directly, and so it removes a hydrogen. And so it breaks a bond with one of the carbon-hydrogen bonds because it's so reactive, and takes the hydrogen away. And when it takes that hydrogen away, you're left with a CH3 free radical because the carbon has gained its electron back, but the electron with the hydrogen has gone with the HCl to form a new stable compound. But that free radical, CH3 free radical, will also seek something else out as well. Now, there's not very much HCl in here, so all there's really left is CH4 and Cl2. But because if you react to CH3 with the CH4, there's no difference because you just remove an H and swap them. You have to react it with Cl2. And as a note, now that I'm thinking about this, you want to realize the initiation only makes a small amount of Cl free radical. So it doesn't react all of the Cl2 into Cl free radical. It makes a small amount, which then starts the reaction going. So you still have plenty of Cl2 in your system to react with a CH3 to form CH3Cl plus Cl free radical. And those two steps are what kind of help propagate and make more of free radicals. And also, as a byproduct, make more of the product that you're desiring, which is CH3Cl. Once you get an abundance of these free radicals, they start colliding with each other. And this is where termination happens, because when two free radicals collide with each other, they form a normal bond and they become stable. And so you might have a situation where two Cl free radicals combine, or two CH3 free radicals combine, or a CH3 free radical and a Cl free radical combine. All of these are acceptable. You don't need to write all three of them. You just need to know one of these terminations. And these two propagations. And this one initiation, excuse me. So the initiation and the propagation ones are, I think, the more challenging ones. Once you've identified what the possible free radicals are, termination is easy because you can pick any two free radicals you make and combine them together to form the final product for whatever product you want. The product in the termination step doesn't have to match the products in the overall reaction, because in this type of reaction, it's kind of a scatter of reactions that you're just trying to get one of them to occur that makes the desired product. So you're going to get a bunch of byproducts in here, and that's okay. But is this still the best way for the reaction to occur to create this species right here, the halogenoalkane? Which has a very polar bond, which makes it more reactive. So that fact that you've added a halogen into an alkane allows it to go further down the reaction chain and pathway and do more and more things to it. And that's what we're going to talk about next. So focusing on initiation, propagation, termination will come as a byproduct that you can figure out whatever way you want. Make a note that you'll never have hydrogen as a free radical in a propagation step. It just doesn't work that way. And so if you end up making a hydrogen free radical, you did something wrong. So yes, this is the overall reaction, but your steps will not add up to that overall reaction. Like, because I said before, you're going to have like byproducts in here. You're not only going to make CH3Cl and HCl. You're going to make a bunch of byproducts. And so once you're done with all the reaction, you'll end up having to find a way to separate the CH3Cl out from the other byproducts and things like that. But we're not going to go into that detail right now. Okay. Questions about that? because the next step of this is taking that halogenoalkane and then undergoing a new type of reaction. Okay, and this is called nucleophilic substitution, where you take the halogenoalkane and we convert it into an alcohol by substituting the nucleophile. Nucleophile, remember, means how do I want to say this? It is electron rich. Okay, so it is seeking a positive nucleus, and so these nucleophiles in this case will be OH minus. That's a nucleophile that's going to substitute for the halogen in your reaction. And for higher level, when we after our break, we will talk about this and diagram all of this out. But for our purposes now, the idea that you want to know for SL is that when you have a halogenoalkane and you react it with sodium hydroxide, for example, it could be potassium hydroxide, it could be any group 1 or 2 hydroxide, as long as it dissociates 100%. What will happen is that the... Oh, sorry. Yeah, Zara.
I had a question. What exactly has to dissociate completely again? Sorry.
Oh, the hydroxide compound.
All right. Okay. Thank you.
Yeah, no problem. So because you can't just add hydroxide to the system, so you have to add like a salt that has a hydroxide, so like sodium hydroxide, potassium hydroxide, things like that. So when you put it in the solution, it should dissociate completely because it's a strong base. And the OH minus that's what's really going to involve in. The Na plus doesn't do anything itself. It's kind of more of a spectator ion. It provides the OH minus to initiate the reaction, but it itself doesn't actually change throughout the whole system. And so that has to dissociate so the OH can attack this compound and then make the alcohol by substituting the Cl out for an OH in this compound. And that alcohol has a functional group that we call the hydroxyl group. Okay, they are going to be very particular about you saying that the hydroxyl group versus saying an alcohol, because the hydroxyl group is the actual functional group. The alcohol is a class of compound. Okay, and again, we said the ending is OL in here. So you need to know whether SL or HL to know that this is a nucleophilic substitution reaction, because they will ask you types of reactions on the short answer. So we talked about combustion, we've talked about free radical substitution, we talked about nucleophilic substitution, and we're going to go on to our next type of reaction after this. Okay, because that alcohol allows us to make newer functional groups as well through a process that we call oxidation of alcohols. Okay, and so what we're doing here is now we're oxidizing those alcohols, and when we say oxidize, we mean it in the sense of increasing the carbon's oxidation number by adding oxygen bonds to that carbon. That's what we care about. Removing hydrogens from the carbon and adding oxygen bonds to it to make it more oxidized. And so a few things we need to focus on, ideas that we have to apply in this. We have to apply the degree of alcohol. So identifying what degree of alcohol do I have? Do I have a primary, a secondary, or tertiary alcohol? Because that will affect what products I make. Okay. what is my oxidizing agent? And your oxidizing agent we will stick with is acidified dichromate, meaning H plus with some salt that has Cr2O7 involved. Maybe it's sodium dichromate, potassium dichromate. Again, it doesn't really matter what the metal is. It's just the dichromate that we need in solution. So usually it's potassium or sodium dichromate. And we also need to know methods of separation, because there will be instances in this pathway where we may need to separate out a compound so that it doesn't react anymore, or we may need to recycle a compound that we need to react more. And understanding the intermolecular forces will help us use the techniques that we know about separation techniques to isolate different compounds or recycle different compounds in our reaction. So these three main ideas are what you'll see in this concept. Okay. So let's draw out our different degrees of alcohols. Okay. We have something like this. And we have something like this. And then we have something like this. Okay. These compounds are all alcohols because they have hydroxyl groups attached to a carbon. But it's important that we identify what type of carbon, what degree of carbon that OH is attached to. And that comes down to how many carbons is attached to that carbon that the OH is attached to. And so if we notice here, this is a first degree because there's only one carbon group attached to the carbon that the OH, the hydroxyl group, is attached to. Here, we see that as a second degree because two carbons are attached to the carbon in question. And last but not least, this one is a tertiary alcohol because the OH is bonded to a carbon that's bonded to three different carbon groups. It doesn't have to just be CH3. It can be a longer chain or whatever, but the fact that it's bonded to three different carbons gives it a third degree or tertiary. Now, what we'll find is that when we add our oxidizing agent that we said before is our dichromate, the first step that occurs is for the first degree or the primary is you remove this hydrogen and you remove this hydrogen from this oxygen, which allows the formation of an aldehyde, okay, with the functional group of a carbonyl, okay, and an ending of Al. So methanal, ethanal, propanal, things like that, you know, are aldehydes because they end in Al. Now, this product can actually keep oxidizing because the carbon's not fully oxidized because you can add one more O bond in here to replace that H. And so if we want to stop here, we have to come up with a separation technique that takes advantage of structural features about these molecules that helps us separate them by physical properties. And the idea here is that this has hydrogen bonding. And this is dipole-dipole. Which means that the alcohol has a higher boiling point because it has stronger IMFs than the aldehyde. And boiling point is a physical property that we can use to separate separate substances apart through the method of distillation. And so if we distill, when this aldehyde forms and it starts to boil off because there's heat being put in here, what we can do is we can redirect that vapor somewhere else and collect it away from the oxidizing agent, away from everything in the flask, and then collect that substance. And then once it's away from everything else, it won't react anymore and it'll stay the aldehyde. So we can collect it in that manner. But if we wanted to continue oxidizing, we will add, question? Okay. If we want to keep oxidizing, because there is potential oxidize here, we can oxidize this all the way to this, the carboxylic acid. Okay. And this has a functional group of a carboxyl group. And it ends in oic acid. And so if you somehow get that aldehyde to go back into the flask and react more and more, it will eventually oxidize further to make a carboxylic acid, which has hydrogen bonding, which means it won't distill off like the aldehyde would. And so what we do to get there is we heat under reflux. Or reflux condenser.
Mr. Trong,
Yes,
did
sir.
you use reflux condenser with like for the alcohol, or do you do that to the aldehyde?
No, you do it with the alcohol. You set it up with the alcohol because the alcohol will naturally produce the aldehyde, and then you want that aldehyde to condense back in to the same flask, so
Okay.
that it'll oxidize more and become the carboxylic acid. So, yes, like if they ask if you're trying to transform an alcohol to a carboxylic acid, you have to do it under reflux to make the carboxylic acid.
Okay, thank you.
You're welcome. No, that's a good question. So yeah, you won't like distill the aldehyde, then reflux condense that. You will always start your setup. Your setup will always have in mind of what product do I want to go to. So before you even set up the whole thing, you're like, okay, I have a primary alcohol. I want to make the aldehyde. That means I need a distillation setup because I need to collect my aldehyde somewhere else because it's going to boil off. If I want carboxylic acid, I need to set it up so that it refluxes and recycles back into the flask so that it will oxidize more. And then once it oxidizes more, it won't evaporate like the aldehyde would. And then I can collect all of that from that flask itself as well. And so your intent is always starting with the alcohol. What setup am I going to choose? A distillation to make an aldehyde, or heat under reflux to make a carboxylic acid? Yeah. Now, with the secondary, you only have one hydrogen that you can really remove from the carbon. And so with that one, it doesn't matter what happens because you can only oxidize it once. And this is our ketone. Okay? And this ketone has a functional group of a carbonyl as well. And this one ends in -one. In this case specifically, this would be propanone. Notice I don't put the number here because with propanone, there's only one possible place it could be because any other carbon it would be on is an aldehyde. So they choose not to write the number in there because it's redundant. And with the tertiary, because there's no hydrogen to remove from the carbon, there's no reaction that occurs in this process. And so there's no way the carbon can oxidize here because it can't lose any hydrogens. So visually, what you're looking at here is if the oxidation occurs, what's going to happen is that Cr2O72 minus is going to go to Cr3 plus, which means it's going to change to green. So if the test tube changes color to green when you add an oxidizing agent to it and a little bit of heat, that tells you, okay, there is an oxidation reaction occurring here. So it's either a primary or a secondary. Now you can't, without more information or more techniques, figure out whether it's primary or secondary, but you can identify and eliminate tertiary from your choice, because if it's tertiary, it will stay orange because none of it's going to oxidize. And so you can at least eliminate the tertiary alcohol from contention when trying to identify an unknown. This is one of those kind of visual representations that you need to be aware of and be able to state and identify. Questions about that? Okay. Moving on to our next reaction, because this carboxylic acid and these alcohols can actually undergo another type of reaction. And that is called condensation. Okay. Combining two species together with a small byproduct produced. Which in our case here is H2O. So for our condensation, we're very specific about what types of functional groups are going to combine together. And R2 will be an alcohol plus a carboxylic acid using sulfuric acid to form what we call an ester. Okay. So the alcohol and the carboxylic acid combine together to form an ester. And so you could have an alcohol like this and a carboxylic acid like this. Okay. And what you need to imagine is, this OH and this H being removed to form water. Now, technically, that's not the oxygen that goes away, but I think it helps you with your naming ideas if you think of it that way. Because really, when you draw it, you don't show which oxygen is which anyway, so it doesn't really matter. The fact is there's an oxygen that links those two things together, and the OH and H from combined between the two is removed as water. So the other two parts here are linked through that oxygen. And so you'll see CH3, CH2, O, C double bond O, CH3. That is our ester. Okay. And we name it as such because when you look at the blue part, this is just an ethyl group. Okay. And this is ethanoic acid. And when you lose that H, it becomes ethanoate. Because every time a carboxylic acid loses a hydrogen, it becomes O8. That's the convention for it. So this is ethyl ethanoate. You always focus on the side that has a carbon double bonded to the O as your O8 part, and the part that's bonded on the other side of the oxygen as your YL part. And so you might have something just to kind of reinforce that. Something like this. The length of the sides doesn't matter. All you care about is the fact that this side is on this side of the oxygen. So it's 1, 2, 3, 4, 5. That's pentyl. And this side with the C double bond O is 4, so that's butan O8. So this is pentyl butanoate. It doesn't matter which side, it doesn't matter if it's left to right or reading right to left. It's good that you circle the part that's attached to the O that doesn't have the double bond O, and that's your first part. Circle the part that does have the C double bond O as your main chain, and that becomes pentyl butanoate here. Okay. Questions about naming ester groups, ester compounds. Okay. We are going to change speeds here to a different kind of branch of reactions. So we've gone as far as we can, starting with a free radical substitution all the way to condensation, going through like 4 or 5 steps. So that kind of pathway chain is kind of over with. The other pathway chain that we want to focus on are addition reactions, and namely what we call electrophilic addition reactions. Okay, and these involve alkenes, because electrophilic means that it is electron deficient. So what it's seeking is a pair of electrons to compensate for its deficiency here, and that comes from the alkene. So that double bond in the alkene is electron rich, and it will seek out other species to bond with, and those are all the electrophiles that you'll see in this next listing here. And so we have we have 4 major electrophiles that we will address. Okay. H2 as an electrophile. This is more specifically what we call hydrogenation. So hydrogenation is when you hydrogenate or add H's to an alkene to turn it into an alkane. And so you might see something like C2H4 plus H2 using a nickel catalyst at about 150 degrees Celsius to form C2H6. You're going from alkene to alkane. So hydrogenation turns an alkene to an alkane. Okay. Second one. Halogenation. Okay. With a halogenation, what you're doing is you're replacing the double bond with two halogen atoms. So instead of having a carbon-to-carbon double bond, you have now a halogen attached to each carbon. In this case here. So notice with halogenation, you're not making a halogen alkane, you're making a dihalogen alkane because you're adding a halogen on both carbons. So there's two halogens attached to it, not just one. So be very careful about that. That's a detail that's important to avoid mistakes. Three. Hydrogen halide addition. Okay. So with this, you're taking the alkene and you're adding HX, which now does make a halogenoalkane because the H adds on one and the halogen adds on another one. So that is your halogenoalkane. So if you want to make a halogenoalkane from an alkene, you just add hydrogen bonded with the halogen you want to add on there. HCl, HBr, HI, whatever you want. The last electrophilic addition we'll do is with water, which we call hydration. Now you do want to know the catalyst here is your sulfuric acid. It helps the reaction occur so that you can produce the alcohol. So you can go from an alkene to an alcohol directly as well by adding water and sulfuric acid to an alkene. Now, what's nice about this for SL is that for these last two, hydrogen halide hydration, you are adding two different things, so it doesn't matter where you add them on the carbon. But for SL, everything's symmetrical, so your structure doesn't change depending on where you add it on the across the double bond. It'll still be the same structure. With HL, it will matter because in HL, you'll have asymmetrical alkenes, where you have to use Markovnikov's rule to identify the major and the minor product. But for SL, you will always have the same product, no matter what, because you have symmetrical compounds. Okay. Now, this is still the same idea of electrophilic addition, but it's not as much of an electrophile situation as the other ones, the ones we just outlined, and that's polymerization. So in this case, because we're using addition reactions, these are labeled addition polymers. So they're adding to each other to create this long repeating unit chain. And so they might give you a monomer like this. One single molecule that is used in the polymerization process. And what happens is when those monomers bunch up under high pressure and high heat, is that this double bond creates bonds between all the monomers and creates this long chain of repeating units throughout this entire thing. So that's our monomer here. And that will make our polymer. And generally speaking, the IB asks you to draw 3 repeating units. So that means that for your purposes here, you're going to have 6 carbons in the middle here, because 3 repeating units, the only carbons that should be in the main chain, in the middle chain, are the carbons that are double bonded together. It doesn't matter if you have CH3 groups hanging off there; those don't become part of the main chain. They get pushed aside up top or on the bottom for the structure. So don't worry about that. So you will then fill in the rest of the groups here to show a repeating pattern here. So this is your repeating unit, because that's the section that gets repeated over and over and over hundreds of thousands of times in the polymer itself. So there's a difference between the monomer and the repeating unit, and a section of the polymer. Notice I have that end subscript there with parentheses and the bonds going through it. That implies that it continues in both directions. But usually the IB will ask you to just draw 3 repeating units of the polymer. Okay. Questions about that? Okay. Let's talk about a unique structure in SL terms for right now and HL terms a little bit later, and that is benzene. Okay, benzene is a very unique structure with resonance in that ring structure that it has, and so what you see, oops, oh no, in that resonance structure of benzene, okay, it has resonance, which means it provides added stability, okay, and because of that, it's dependent on all 3 C to C double bonds. It reacts differently than normal alkenes. Because you can make an argument, well, it has double bonds, so I can do alkene addition, electrophilic addition to it, and replace one of the double bonds with a group. But the idea is that if you do that, you'll destroy the stability of the structure, and then it makes it not stable. And so what we do here is no electrophilic addition, because you can't add anything to that benzene. What you do is electrophilic substitution, where you replace an H in the species. So the benzene itself will maintain its entire ring, but it will replace one of the H's that are attached on the carbons here with a different group. And that allows it to get more reactivity but not destroy its 3-ring alternating structure. And so you would see something like for the nitration of benzene, again, for SL you don't need to know like the mechanics behind this, but the idea is that through this process you will create, instead of having an H on one of the carbons, you'll have an NO2 group. So your substitution. And that substitution is what makes benzene be able to be more reactive and combine with other things. But you can't just add something to the double bond like you would with a normal alkene because of the stability of the ring structure here. questions on that? Okay. IHD and then isomers are going to be kind of our last two major topics for SL, and then we'll go into the HL material. Okay. IHD is index of hydrogen deficiency. Okay. The index of hydrogen deficiency determines how many H2 molecules are needed to create a straight chain alkane. So this eliminates rings. This would eliminate rings. And it would eliminate double bonds, double and triple bonds. Okay. So the IHD is used for that. Okay. And again, for those of you that don't remember, IHD is 2C plus 2 minus H plus N minus X over 2. Because the 2C plus 2 implies how many normal hydrogens you should have on there. Like theoretically, that would be the maximum number. And every H and every halogen acts like a hydrogen. So it's a single bond to a carbon, so those are okay. And then the nitrogen makes it kind of different because it doesn't have like as many hydrogens possible bonded to it because it only has 3 bonds on center. So instead of doing 2C plus 2 there with the nitrogens, we treat the nitrogens separately as one additional hydrogen that would be on the structure for this. Okay. And so if you take something like C4H9OH, well, this is 2 times 4 plus 2 minus 9 or minus 10 plus 0 minus 0 over 2. So this has a IHD of 0. So what that tells you is that there are no rings and there's no double or triple bonds anywhere in the structure for this. So what you end up having for C4H9OH is, generally speaking, something like this, an alcohol. And this is butan 2-ol. So this is the OH being on the second carbon of the chain, and it's a 4-carbon chain. That would be butan 2-ol. Notice again, no rings, no double bonds or anything like that, because if I have any double bonds or any rings, I don't have the sufficient number of hydrogens to meet my formula. Okay? And you might also have something like butan 1-ol. Where the OH is on one of the ends. And you could have something like this. Okay. 2-methyl propan 2-ol. Okay, again, no rings, no double bonds, branching, but that branching doesn't affect how many total hydrogens you can have. And you also want to consider, this is where we introduce the idea of ethers. Let me make a different color here. Okay. Ethers have a carbon oxygen to carbon linkage inside the species. And they have a different special notation for naming as well, which we're going to talk about here. So, for example, I could rearrange this that would still be C4H9OH. 10 H's, 1 O, 4 C's. And the way you name this is you always go by the shorter structure, shorter part chain first. And you attach the O to that. It doesn't matter if it's on the left side or the right side, whichever is the shorter chain, that becomes oxy. So this is methoxy propane. The longer chain gets its normal alkane name. So you treat the methoxy as a functional group that's attached to a main chain. So methoxy propane would be the example here. And there's other ethers as well you could do here. Ethoxyethane is another one. I guess that's the only other one, really. Ethoxyethane in this case, because you only have 4 carbons, so you can only move them in one place. But those are the main kind of isomers that we have. C4H9OH isomers. And these we're talking about are structural isomers. So the names change here. Okay? So if you're naming it and your name changes, and I don't mean like cis, trans, or E or Z in HL, I'm saying the actual numbers or the function group names change, that's an indicator that you have a different structural isomer here. Questions about that? Okay. Additional function groups that you need to be familiar with, even though you don't have reactions with them. So these are function groups that that you have to identify in unknown compounds and stuff like that. And so okay, things like an amine. Okay, an amine is when you have that NH2 group, or like an NH with another R group, or an N with 2 R groups on it. Those are all amines. So if you see an N with within a carbon chain and things like that, that's an amine group. And you just be identifying that as a functional group here. You might also have a carboxamide. A carboxamide is when you have a carboxyl group, but instead of an OH or an O on the other side of the carboxyl group, you have an N instead. And so this whole thing right here is called a carboxamide group. So if you see a aceto bond O and then an N connected to it, that's a carboxamide. And a nitrile, that's C triple bond N. So if you see those, they might just be a 1-mark question identifying the functional groups present in the structure here, so you need to know these, but they don't get involved in any of the types of reactions you need to know. So like if you're really trying to prioritize things, I would focus on the functional groups that are involved in the reactions and things like that, and this would be kind of an afterthought if you're trying to prioritize with your kind of month left in this, that these functional groups are not as important for this as alcohols, carboxylic acids, esters, aldehydes, ketones, and things like that, where those are actually being used in reactions. like I said, because of the time restraints here, um, we are not be able to cover every single detail of topic 10. So there are things that I've not talked about that I would strongly suggest you look over on your own. Homologous series for one, and physical properties of function groups, like what type of IMFs, the strength of them. We had a chart in our notes that identified the strength ranking of the different function groups present in structures, because you need to understand how those impact your boiling point, your viscosity, and things like that. So your physical properties. And so those are the two main things that I think that we didn't cover in SL that we need to cover, that you would need to revise for this unit. Okay. Any questions about anything we've covered so far today? Okay. That will be the end of our topic 10 review. In our separate video, we will cover our topic 20 review, which is the higher level portion of organic chemistry.